I'm really excited to be here today to talk about quite a new topic in the world of HPC. Quantum computing has come a long way over the last few years, and it's really exciting to actually be able to talk about things that we're starting to be able to do with these systems. So this was joint work with BP looking at exploring applications of these systems for a molecular conformation generation. I'm going to start by saying a few words about Orca. So we're a full-stack photonic quantum computing company. We have offices in London and also here in Texas in Austin. We have commercially available quantum processors now with 10 systems deployed to different customers around the world. And we focus on a couple of things. One thing is making sure that these systems can fit into the physical and software requirements of data centers. And we also work on developing applications of these systems for generative machine learning. If you're wondering, this is what our systems actually look like. This is a picture of me and a colleague next to one of our systems at the Poznan Supercomputing and Networking Center in Poland. So in this case, what you don't see is on the edges of the pictures on both sides is the traditional HPC environment. You have an Ethernet cable at the back that connects to it. It fits into the rest of the Slurm-based scheduling of this HPC environment. And we used this for a recent demo of a hybrid quantum classical biomedical use case in collaboration with, PSNC and also NVIDIA. Now, in this project, Orca and BP worked together to investigate a hybrid quantum classical algorithm for molecular conformation generation, which is an HPC workflow in chemistry. Kind of taking a step back, broader motivation for this was to develop use cases of quantum computing in the energy industry, trying to identify what the opportunities are for quantum computing, and also developing workflows for future HPC AI quantum workflows. So as we're seeing AI taking a larger and larger importance in HPC, looking at how and where quantum computing can fit in. So the problem we chose to focus on was the molecular conformation problem. This problem is that molecules can exist in different conformations, which is where some parts of the molecule can have different angles compared to other parts of the molecule, like in this example here. Some conformations are more stable than others. They have lower energy. And identifying these stable or low energy conformations of molecules is important to be able to understand their chemical properties. And this is useful for applications for fuels, lubricants, etc. Trouble is, the number of possible conformations scales exponentially with the number of atoms in the molecule. And so there are toolkits out there to try and calculate the different conformations of a molecule, such as our RDKit. But because of the exponentially large search space, they start to struggle if the molecule has more than around 15, 20 atoms. So we had to look at first of all, at how machine learning can help address this problem. And then the second step was, how can then quantum help a machine learning approach? So in the machine learning approach, the motivation here is that, machine learning models are strong at producing patterns in complex spaces. So good at producing text, for example, with ChatGPT as an example, image generation too. So the motivation here is instead of using a physical model or toolkit like our RDKit, we can train a machine learning model that generates the types of conformers we're looking for. And this is something people have looked at before with graph neural networks and diffusion models too. but their performance is still limited, and training resources, time, energy, cost, and producing the data sets you need for this can be a problem. So the question is, can a hybrid quantum classical generative model provide an advantage here? So the opportunity we have is that current quantum computers are still small scale, but they can already solve some tasks faster than classical computers, some specific tasks. And in particular, they have already achieved an advantage in being able to sample from some classes of probability distributions. Now, if you think about different types of sampling problems out there, a really simple one for a traditional computer is just simulating random coin flips. So that's sampling from a uniform distribution over bit strings. That's an easy computational task. A harder distribution to sample from that requires a lot more computation is sampling from the pixel values in a large image that correspond to pictures of cats and dogs. That requires a lot of GPUs, lots of training, lots of data. Another type of really hard distribution to sample from that takes a long time is sampling from the outcomes of Monte Carlo simulations of different kinds of physical models. What's interesting is we're now in a position with quantum computers to be able to sample from some types of distributions faster than we can with classical computers. Kind of as a Venn diagram here, if the black circle is what you're able to do with traditional computers, the blue circle is what you'll be able to do with long-term, large-scale, fault-tolerant quantum computers. Where we are now is kind of this green circle, where we're starting to be able to expand the capabilities of traditional computers and going beyond them. So the type of photonic, the type of quantum processor that we consider for this work is photonic quantum processors. The way that these work is you send in identical single photons, the red dots there, into a complex programmable circuit. The photons interfere with each other in the circuit. This produces a large quantum superposition state, and then you measure where the photons leave the circuit. So this is not a universal a computer. It's not going to replace your laptop or HPC anytime soon, but this is an accelerator for being able to sample from specific classes of distributions. Advantages is that these kinds of systems can operate at room temperature. So for this work, we used a simulated processor, which limited us to size 32 distributions. That's kind of roughly the crossover point where you're starting to see that this task, that sampling from these distributions can take a long time on a traditional computer, and where you're starting to, and that's also roughly the scale that current quantum processors are at. But this is still quite small scale, so in order to be able to leverage this in a generative machine learning task, we need to combine this with traditional computing. And the way that we did this is by using these kinds of distributions that we're able to sample faster on a quantum computer. We use those distributions as the latent space in a generative adversarial network. So taking a step back, the task of being able to generate good conformations of molecules is also a sampling task. If you have a data set of molecular conformations, those are individual samples from the distribution over all the relevant conformations of a molecule. So that's kind of the data that you have is kind of those red dots in the distribution you're trying to learn, which is that outline on the top left. So the way that you learn this distribution using a generative adversarial network is you have two neural networks, a generator and a discriminator, trained against each other, where the generator is trained to produce conformers that look like the actual ones in the data set. the discriminator tries to tell the difference between the generated conformers and the actual ones in the data set. And the generator tries to generate conformers that are good enough that they will fool the discriminator. Now, an important component here is that what the generator actually does is it converts an initial latent distribution into the distribution of generated conformers. So the generator learns to map one initial distribution, which can be quite small, to the distribution over the molecular conformations, which can be quite large. What you're trying to do is, after training, you're trying to make sure that the distribution the generator has learned to produce is as close as possible to that outline in the top left. So that's kind of schematically shown in the right there. You're trying to learn a blue outline there that's as close as possible to the black one. Now, this initial latent space that the generator learns to map to the actual data distribution you're interested in plays a really important role. It's been shown, for example, that just being able to add trainability to it can lead to a 30% improvement. So what we did was we used a photonic quantum processor to produce this latent space. So like in practice, it's quite easy to do. This can be done with an extension to PyTorch, so it's programmable within a PyTorch environment. The motivation here is that being able to produce these distributions that kind of go beyond what traditional computers can efficiently produce, like having that option of going beyond the limitations of traditional computers, can make the generator learn better quality conformers compared to just having a purely classical distribution at the start. And we found that on several types of data sets that this approach can lead to an advantage. So this is the main tool that we used to approach this molecular conformation problem. So this is the problem setting we looked at. To start with, work with a simple data set of molecules that just have carbon and hydrogen atoms, alkanes. You represent this as a data set of where the different atoms are in the molecules and what the different angles are between those atoms. So we used a physical solver RD-kit to produce a large a data set of 30,000 conformations of these molecules with 14 carbon atoms. What you see is that kind of like these sets of angles between the different carbon atoms in the molecules are quite peaked around certain values. And we used a graph neural network as both the generator and the discriminator in the GAN. So to investigate the potential of these hybrid quantum classical generative networks, we looked at a couple of questions. One of them is just, can we learn the correct distribution of angles in this data set? That's question one. Second one is, well, how good are these for producing specifically low energy conformers? So what you have on the graph on the left there is the distribution of angles you have in the data set, a set of peaks around certain values. We have on the right there is the distribution of the energies of the conformations in this data set. So in this case, we just produce lots of random conformations without really caring too much about their energies. But what we'll be trying to do is see how well we are, how good we are at generating conformations with specifically low energies. First thing we did is, so we trained our hybrid GAN model, and we looked at the distributions of angles that we get from the conformations generated this way. And the real angles here in orange, the distribution we generated was in blue. So we do get the same general features, the four kind of discrete sets of angles appearing in this data. Okay, so that's great, but how do we tell if actually how do we tell how good this is? It's actually quite hard to tell for a generative model how good your results are going to be, because lots of the conformations you'll be generating may not be in your original data set in the first place. So what we did is we kind of used this graph here, like trying to try and tell how the distribution we're producing compared to the actual distribution. So we compared our hybrid quantum classical GAN to the exact same neural network architecture where you just had a purely classical latent space. And we produced this table here, which is like how close we are to the correct distribution of angles. And this is over 3 different train test splits and averaged over 20 random seeds, so we could get really statistical results. And what we found is that, so in this case, a lower number means that the generated distribution is better than the, a lower number means that your generated distribution is better. And we found in this case that there was about a 20% improvement in just swapping out the initial classical distribution in your GAN for a quantum distribution. The second thing we looked at was the conditional generation problem. So in this case, it was for a given isomer, comparing the distribution of energies of the generated conformers between the hybrid GAN and the purely classical GAN when you're trying to produce conformers with a specific energy. So in this case, we normalized the energies. We wanted to, we conditioned the GAN to produce conformers with just specific energies, in this case of 0.2. And what you get is a distribution like this one. So in this case, the orange data set is the distribution from the entire data set. Blue is the conformers we were generating from the hybrid GAN when we were targeting an energy of 0.2. So there's a bit of a spread, but most of the conformers we were generating are at the correct energy. And this is great. It means that you can use this approach to kind of like start to produce the lowest energy conformations of molecules that you're actually interested in. Now we compared the hybrid quantum classical approach to the classical approach. So on the left there is the same diagram. We're trying to generate conformations of molecules with a target energy of 0.2. When you used the quantum distribution as a latent space, we got this like quite peaked distribution around the target value. And when we used kind of the standard, most commonly used classical distribution, we had this much more spread out distribution. So this shows that the hybrid approach produces conformers that are a lot closer to the target energy. Then on the right, we kind of repeated this process for lots of different target energies, and we plotted the spread of the energies for those different generated conformers. So what you're trying to do is produce conformers that are as close to the blue dashed line as possible, right? If you have a target energy of, say, 0.4, you want your generated conformers to have an energy of 0.4. And blue was what we were getting from the quantum distribution. Orange is the traditional Gaussian classical distribution. And we found also in this case that essentially over all the energy ranges, we were doing a lot better with the quantum distribution versus the Gaussian one. And especially for the very lowest energies, the ones we were really interested in, we were producing conformers that were 50% closer to the target low energy compared to the classical distribution. So in conclusion, what we found is that this hybrid quantum classical model outperforms a purely classical model for molecular conformation generation. And this is really interesting because essentially all we did was like keep the exact same neural network architectures, and we just replaced the initial small-scale latent space distribution. It's a scalable approach. Even though the initial latent space distribution is quite small, it's the size of what you can produce with quantum processors now. This is actually able to make quite a meaningful difference on the performance of the overall neural network, even if it's quite a large neural network. So taking the broader view, what we've shown is that there's potential in using quantum computing to complement and improve AI methods in computational chemistry. We've demonstrated a workflow that combines like quantum computing, and AI for a problem that is a relevant HPC problem. And kind of as next steps, we'd be interested in, well, expanding this kind of work to more complex data sets with larger, more realistic molecules, and also exploring applications of like hybrid quantum classical generative machine learning for different classes of problems, also within the energy space. Oh, thank you for your attention.
Thank you, William. That brought us back on time, actually.
Cool.
Well, quick comment on what's next, and then we open up for questions. We will be setting up for a panel, like I said at the beginning of the session. We had one presentation drop out, so we'll supplement that with a panel discussion. So maybe we can start setting up the chairs for that. In the meantime, since we have a couple of minutes until that is done, does anybody have a question for William?
If I understand correctly, like you're creating this latent space using quantum processors, and then you showed the comparison with the Gaussian distribution, right? Like if you use just a Gaussian versus this multimodal like probability space from which you're sampling. Is that the reason why you are seeing this advantage? And that builds me to my question, like what if instead of a Gaussian, you used some like arbitrary probability distribution which has like multiple like peaks, right? Would that like help? Did you try something like that?
Oh, it's a really good question. So yes, so in this case, the difference in performance is entirely due to just using a different latent space. I didn't show it in these slides, but we also looked at some different types of classical latent spaces, and also in this case, the quantum distribution consistently gave an advantage.
And just to follow up, can you comment on the training times if you use the quantum version of it versus classical?
So actually, what's quite good with these types of generative models, so with GANs, but also flow matching models, for example, is that the quantum processor itself like isn't a bottleneck in the data. So so essentially you're able to run this workflow with only minimal overhead from using the quantum processor. Also in this case, we were using a simulation of the quantum processor, not too far from that crossover point where using a quantum processor is going to be faster than actually doing it on traditional computing. So actually, so the main answer in that case is that there's pretty much no overhead compared to just using a classical distribution, where it's very small, just a few percent.
Thank you.
Let's thank William again.